So today's lecture, we're solving trig equations. So let's start with a simple one. Let's start with a very simple one, guys. Shh. Ruhan, was it all good? Ruhan? All good? Okay. Let's start with a simple one, sine x equals 1/2, and solve for x, sorry. Okay. So this is a question that we've seen a lot in chapter 4, right? We go to our unit circle, and we just think about which points on the unit circle have a y-coordinate of 1/2, right? Because the sign of a point on the unit circle is the y-coordinate. So we think about which y-coordinates have 1/2. And if we look and think about our unit circle, that's going to be this point and this point, right? So that's pi over 6 and 5 pi over 6. Okay? You can confirm that both of those points have y-coordinate of 1/2. And so sine of pi over 6 is 1/2, and sine of 5 pi over 6 is also 1/2. Okay? So we might be tempted to just write x equals 5 pi over 6 and x equals 5 pi over 6. And we might be tempted to just be done with it. But unfortunately, we would be wrong because there are actually an infinite number of solutions to this equation. So how do we figure out which infinite solutions are there? Well, the logic behind that is that we think back to the properties of the sine function, and we recall that the sine function has a period of 2 pi, right? So that means as x changes by 2 pi, we're going to return back to the same value of sine. In other words, as we go another 2 pi around the unit circle, we're going to return to the same point, which means that the sine value will stay the same. And so not only is pi over 6 a solution, but we also need to include pi over 6 plus 2 pi, right? Because it has a period of 2 pi. And not only pi over 6 plus 2 pi, but also pi over 6 plus 4 pi, and pi over 6 plus 6 pi, etc., right? And not only those, but also pi over 6 minus 2 pi, minus 4 pi, minus 6 pi. And so the way that we use to write all these solutions is we just say that x equals pi over 6 plus 2 pi n, where n is some integer. And also 5 pi over 6 plus 2 pi n, where n is some integer. Okay? So that means we're including all these solutions, pi over 6 plus 2 pi, and also 5 pi over 6, and 5 pi over 6 plus 2 pi, and plus 4 pi, and so on. And also minus 2 pi. Okay? And so we can kind of consolidate all this infinite solutions by just writing plus 2 pi n, where n is some integer. For integer n. That would be our solution. Okay, any questions? Any questions? N is some integer. Could be -1, could be 0, could be 1, 2, 3, 4, 5, 6, 7, 8. Am I done? Okay. I'll show you guys another way. Let's think about the graph, okay? The graph of sine. Hopefully it's not traumatizing, thinking about sine graphs.
Wait, can integers be negative?
Yes. Okay, right? This is the graph of sine.
Ooh, nice one.
Yes. Okay, and when we think about like what values of x cause sine x to equal 1/2, we're just thinking about the intersections of this graph with y equals 1/2, right? So this line, all the intersections of this graph with this line would give us those values where sine x equals 1/2, right? And so here we have pi over 6, here we have 5 pi over 6. And you can see that this is a single period, right? This interval here is a single period. And you see how within every period of the sine graph, there are always going to be two values that take on that value of 1/2. But then we also need to include, the next one, right? This value here. Or if we extended it a little bit, this value here as well. And you see how that's just, this one plus 2 pi, right? And this one plus 2 pi. And so on and so forth. Okay, so every period of the sine function, you're going to have two solutions, but you need to also add 2 pi n for each of those solutions to accurately account for all the infinite solutions that are there. Any questions?
Do we need to still graph?
But I know how to graph it.
Don't need to graph it, just need to do the algebra. But I'm just showing the graph just so you guys have some intuition about it.
So the final answer is the thing box. Then.
The final answer is the thing in the box.
Well, is it mark it wrong if we don't have like the n?
Yep, it's wrong if without the n.
What if we put x? Like they have the n. Those any variable.
N is the standard. If you use n, people will automatically know that it's an integer. That's just a mathematical convention. Okay, let me give you some rules. So whenever you have an equation with sine, cosine, secant, or cosecant, for these four functions, you're going to have two solutions for every period. Two solutions and plus 2 pi n. Right? Similar to the previous example, we had two solutions for sine x equals 1/2. We had pi over 6 and 5 pi over 6. And then for each one of those, we had to add 2 pi n. Right? The period is 2 pi. For all four of these functions, the period is 2 pi. And that's why we add 2 pi n. However, for tangent and cotangent, what's the period for those?
1 pi.
Yeah, just pi. And so for those, you're only going to have one solution. Only one solution, and all you need to do is add pi n, not 2 pi n. Got it? So, say you had like tangent x equals 1. You would use the unit circle, you would just find that x equals pi over 4. And then to get all the infinite number of solutions, you would just add pi n. So this would adequately account for all the possible solutions. Right? You can think about it. On the unit circle, which points give you tangent equals 1? It's this point and this point. So that's pi over 4 and 5 pi over 4. But this 5 pi over 4 is already accounted for within this pi over 4 plus pi n, right? Because pi over 4 is just pi over 4, 5 pi over 4 is just pi over 4 plus pi times 1. So that's the solution for n equals 1. So we only need to account for a single solution and then just add pi n, or tangent and cotangent. Okay? But if you're confused, just memorize these rules. Sine, cosine, secant, cosecant, you have two solutions, add 2 pi n. Any questions? No questions? Yeah, Liam?
It's not pi or 5 pi 4, or is it 5 pi?
It is 5 pi over 4, but that's encapsulated within the plus pi n,
Okay.
right here.
Oh.
Because 5 pi over 4 is just pi over 4 plus pi times n equals 1. Okay, let's do a quick example. Let's do sine x plus root 2 equals negative sine x. Okay? So for these kinds of equations, our goal should always be to try to isolate sine in some way. Or whatever trig function we encounter, we want to isolate it. And so if I move the signs to the left side, I'm going to have 2 sine x. And then I move the root 2 to the right side. So 2 sine x equals negative root 2. And then I can divide both sides by 2. And I'll have sine x equals negative root 2 over 2. Okay, so try to do some simple algebraic manipulations. Get the trig function to one side. And have it isolated. Got it? And then we're going to go through the same process that we usually do. we're going to go to the unit circle and think about which points on the unit circle give us a here y coordinate, right? Which points on the unit circle give us a y coordinate of negative root 2 over 2? That's going to be this point and that point. Right, y coordinate of negative root 2 over 2. And so we know it should be a multiple of 45 degrees, or pi over 4. And so this one is 5 pi over 4, and this one is 7 pi over 4. All right, pi plus pi over 4, and 2 pi minus pi over 4. All right, very similar to chapter 4 stuff. And so we would write our final answer as x equals 5 pi over 4 plus 2 pi n. Right, and that would account for all the infinite solutions for any value, for any integer value of n. And then our second group of solutions would be 7 pi over 4 plus 2 pi n. And that would be our answer. Any questions? Hmm? Yep. Any questions? Next one. Let's do 3 tangent squared x minus 1 equals 0. So the logic here is very similar. We want to try to isolate the tangent, but the difficult thing here is that we have a square, and so we need to be very careful because anytime we square something, we're going to have two solutions, right? A positive one and a negative one. Okay, so if you isolated tangent, you would get tangent squared x equals 1/3. But then when we take the square root, we need to account for both the positive and the negative solution. So we would have tangent x equals not just positive, but plus or minus root 3 over 3. Right? 1 over root 3 is root 3 over 3. And then we do a plus or minus because we need to account for the negative solution as well. Any questions? I took the square root of 1/3. Any other questions? Okay, so now we actually have two different solutions for the tangent, right? So we have to split up into two cases. We'll have case 1 is tangent x equals positive root 3 over 3. And then case 2 is tangent x equals negative root 3 over 3. Okay, any questions? And so then we would go back to our unit circle, try to figure out which value gives us root 3 over 3 for the tangent. And we would discover that x equals pi over 6. And then because it's a tangent, we know the period is pi, so we would just add pi n. So the solutions for case 1 are x equals pi over 6 plus pi times n for some integer value of n. Case 2 is very similar. We would have x equals negative pi over 6 plus pi n after you look at the unit circle. Okay, any questions? So these examples are just gonna, same concepts, just get progressively harder. Any questions up to here? Let's do the next one. Let's do an interesting one. Oh, hey, at least today I'm just using x's, right? 2 sine squared x plus 3 cosine x minus 3 equals 0. Okay, so we immediately look at this and don't know how to do it because we have two different kinds of trig functions in the same equation. And so when we have two different kinds of trig functions in the same equation, it's actually not possible to solve. And so we have to think about some clever strategies for how to make this all into one type of trig function. And it turns out that's not too hard because we have identities on our side, right? We're able to convert this sine squared into a 1 minus cosine squared, right? Using the Pythagorean identity, because sine squared plus cosine squared is 1, and so that means sine squared equals 1 minus cosine squared. So if we make that substitution, we can successfully convert everything to cosines, which is very desirable. So I'm going to make that substitution, so I'll have 2 times 1 minus cosine squared x, right? Just replace that and keep everything the same. Plus 3 cosine x minus 3 equals 0. And then after I expand this and combine some terms, I'm just going to be left with negative 2 cosine squared x plus 3 cosine x minus 1, which is a quadratic equation, right? Any questions about how I got here?
Quadratic equation, squared, normal. Oh, gotcha.
Right, so if you guys think back to chapter 3, you might remember those equations where we had like e to the 2x minus 5 e to the x plus 6, right? So the concept is very similar. We have a quadratic of a function, and in this case, the function is not e to the x, but the function is cosine of x, okay? And so we're actually able to factor this. If we used whatever factoring method we found most helpful, we would factor this out. I'm going to factor by grouping. So I can change that 3 into a 2 plus 1. And then after I factor this, I'm going to get negative 2 cosine x plus 1 times cosine x minus 1. Okay? I just factored the quadratic, right? If you're confused, you can make a substitution. You can say like y equals cosine x and then make that factorization. Any questions? Any questions? Yeah. Here? I skipped a step. 2 times 1 combined with the negative 3 here gave me negative 1.
What did you do after that? I don't get how you got 2 causes. Or 2.
I'm confused by the question.
Never mind, I got it.
Okay, and then once we have this factorization, we know that whenever we have 2 factors multiplying to 0, at least one of them must equal 0, right? And so we can once again split into 2 cases. Case 1 is that negative 2 cosine plus 1 equals 0. And case 2 is cosine x minus 1 equals 0. Right? I split it into 2 cases depending on which factor equals 0. And then this simplifies to cosine x equals half, and this simplifies to cosine x equals 1. And then I can go through my normal process of solving, and I would find that for case 1, x equals pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. And then for cosine x equals 1, I'm going to have x equals 0 plus 2 pi n. And then 0 is the only solution. Yes?
What if it's the same, like it's cosine plus cosine? Then you would have to
What's cosine plus cosine?
like the homework or the like the third problem. It's like 2 cosine squared of the same as this problem, except, like.
Just factor, and you'll get some kind of expression with two factors, and then simplify.
Okay, but like when we're factoring, like the reason you made it 1 minus cosine is so the cosine would, like, so they can combine, right?
What's 1 minus cosine? I don't see that anywhere.
On the board, the second step, or I guess,
You mean 1 minus cosine squared?
yes.
Yeah. So on the classwork, you won't need to do that step because they're already in cosines. You can just directly factor the classwork question.
Okay.
Any other questions? Okay. So that is generally sufficient. Never mind. There's one more thing I should explain.
Wait, can you hold it for a second?
Okay. Let me quickly go over something else. This is pretty straightforward, but I need to explain it. What happens when we have a trig function of a multiple angle, such as in classwork part D, right? So let me give you an example. Let's say we have 2 cosine of 3x, that's a 3, 2 cosine of 3x minus 1 equals 0. Okay, we would go through the same process. We would try to isolate the cosine, and then cosine of 3x would equal 1/2.
So x equals 1/6.
Then we would solve for 3x. We would go through the same process and try to figure out what 3x equals to. We would have 3x equals pi over 3 plus 2 pi n, or 3x equals 5 pi over 3 plus 2 pi n. Okay, so same exact thing as before, except now it's 3x. And so to solve for x, we just divide the whole thing by 3. Okay, so we'll have x equals not pi over 3, but pi over 9. And then plus not 2 pi, but 2 pi over 3 n. And then the second solution would be 5 pi over 9 plus 2 pi over 3n. Okay, so this would be our solution. As you can see, the period has reduced by a factor of 3. Instead of 2 pi n, now it's 2 pi over 3n. And this is exactly consistent with our expectations, because if we recall our formulas from graphing, the period of this cosine function should be 2 pi over b, right? And here b is 3. So the period is actually not 2 pi, but 2 pi over 3. And so this is good. This is what we expect. Okay, so same as before, except now we just divide our final solution by whatever factor we have. Any questions?
Okay, in the end, it just doesn't matter until the very last step. You divide.
Yeah, that's right. Okay, I'm not done with the lecture. You do not have enough information to solve question 2A yet. And then we're almost done. So 2A is very tricky, and so let me do an example to kind of illustrate how you do those. Let's say we had this equation. Okay, quiet please, guys. So this equation is really hard to solve because not only do we have a mix of two different kinds of trig functions, we have cosines and sines, but also we don't have any identities with which we can reduce them into a single type of trig function, right? Because we don't have any identity that can turn a single cosine into a sine, right? We have it for cosine squared, but not for just a cosine. Okay, and so the trick here is actually to square both sides. Okay, this is the trick. Square both sides. Okay, the reason why we want to square both sides is because we want to introduce some sine squareds and cosine squareds, and then we can actually reduce it into a single kind of trig function. So if we expand the left side, right, a plus b squared equals a squared plus 2ab plus b squared. So the left side becomes cosine squared x plus 2 cosine x plus 1. Right, if we foiled that, that's what we would get. And then the right side is just sine squared x. Okay? But this is very good news because that sine squared can be changed into 1 minus cosine squared. Right? 1 minus cosine squared. Got it? Any questions? We want to square it to introduce some things with which we can simplify using identities. After we rearrange terms, we would get 2 cosine squared plus 2 cosine x equals 0. And then we would solve this factors, right? Make sure you factor. You can't just divide by cosine. That's illegal. And then we would split into 2 cases. Case 1 is cosine x equals 0. And case 2 is cosine x equals -1. Any questions? Okay, so first step, we squared both sides. We wanted to introduce some sine squares and cosine squares. And then the second step, we converted that sine squared into a 1 minus cosine squared. Okay? And once we've converted it into 1 minus cosine squared, now the entire equation is written only in terms of cosines. And so this is something we can simplify by factoring as a quadratic. Okay, so I moved the cosine squared to the left side, the ones cancel out, and I'm left with just 2 cosine squared plus 2 cosine x.
Didn't you factor 2 cosine x out?
Not just cosine x.
Sure. Doesn't matter. Okay, any questions? And then I factored, and then the first case is either cosine equals 0, and the second case is cosine x plus 1 equals 0. Any questions? Okay, then the next step, you just solve. Guys, quiet please. You solve, and for the first case, you get x equals, what is it? Pi over 2 or 3 pi over 2.
Wait, hold on. It's 2 cosine x, so it should be pi over 4.
No.
What? Why not?
Just think about it. Okay? And then the second case, if cosine x equals -1, that's x equals pi, right? Okay. Very important. Please listen. Whenever you square both sides of the equation, you introduce extraneous solutions. So you need to go back and check. Must check each solution. Okay? Let me give you guys an intuitive way of seeing why you're going to have extraneous solutions. Guys, let's say we start with a false equation. -1 equals 1. What happens when we square it? We get a true equation, 1 equals 1. So that means we can start with something false, but if we square it, we get something true. So that means when we solve the second equation after we squared it, we're going to have solutions that are false originally. And so that's why whenever you do this step, squaring both sides, you must check the solutions. Okay? So if you plugged in these 3 solutions back into the original equation, you would discover that some of them are invalid. Which one is it? Let me think. It is this one. This one is not valid. That one would give you 1 equals -1. And so your final solutions are going to be pi over 2 plus 2 pi n and pi plus 2 pi n.
how do you check it?
You have to plug it back into the original equation before you squared it. So you can plug it back into any equation prior to the process of squaring it, because that's the problem step. That's the one that introduces extraneous solutions.
Would you have to square it again to simplify it after that?
I don't know what you mean.
How
Square
do
it
you
again?
simplify it after you plug it in?
You plug in cosine, you plug in x equals pi over 2 for cosine. And you plug in x equals pi over 2 for here and see if they match. You do that for all three solutions. Right, so if I wanted to check maybe x equals pi over 2, I would go to the beginning and I would do cosine pi over 2 plus 1 equals, what is that? 1. And sine of pi over 2 is also equal to 1. So I'm good for that one. And you would find that 3 pi over 2 doesn't work. Any other questions? Any other questions? Okay, I have one last thing to say. And that is, sometimes you might encounter things such as tangent of x equals like 7 or something. Okay? Things for which we don't know any solution for off the top of our head using the unit circle. In these cases, we are required to use an inverse function. So we would say x equals arctan of 7. But not only arctan of 7, but arctan 7 plus pi n. Okay, because we also have to keep adding those extra solutions. All right, any questions about that? Sometimes you need to use inverse functions.
Ma, can I just put that all the time?
No. So question 3 on the classwork, it says to use inverse trig functions, but actually it turns out you don't need to. So don't use them. But on the homework, there are 1 or 2 for which you need to do this.